Today, in the series of lectures on the transport phenomena in furnaces, I will be talking on role of refractory surfaces on heat transfer. As in my introductory lecture, I said that a furnace is a thermal enclosure, and a thermal enclosure is formed by lining of the refractory material. So, refractory materials have several functions in the furnace, and one of the important function of the refractory surfaces is to enhance the radiation heat exchange and to keep heat within the furnace. When fuel is burnt in the furnace, flame is produced. Now, heat transfer from flame to the charge and to the furnace enclosure, it occurs by mechanism of convection and radiation, and among them radiation is the most important mechanism. So, it is here today we will be considering what is the role of refractory surfaces on radiation heat exchange and how it keeps the furnace hot. So, now for that let us consider the enclosure which is formed by A1, which is the source, A2, which is the sink, and it is bounded by refractory surfaces whose area is AR. As such, that no radiation energy escapes from the furnace, from the refractory surface of the furnace. So, something like this I can represent is, say this is the source, let us say its area is A1, this is the sink, say whose area is A2, and this is now bounded by a refractory wall, whose area is AR. So, this is the refractory wall. So, on this side this is a refractory wall, area is AR. Now, A1 call as a source, A2 is we call as sink. Now, what will happen? As A1 will radiate its heat, so the total amount of heat, that is Q, if I call this surface is 1, this surface is 2, and refractory I denote it by R, then Q that will be equal to Q12, that is a direct heat exchange will occur. The source will radiate its heat, the rate of Q12 plus, as we will see in the course of the derivation, plus some of the heat will be intercepted by refractory wall, that is Q1R. So, total amount of heat, that plus Q1R. So, now let us derive what is the role of refractory surface in the heat transfer when the refractory surface is present. Now, for that we will make certain assumptions. Number one assumption, each surface we consider each surface is at a uniform temperature, is at a uniform temperature and characterized by T1, T2 and Tr. That is, T1 is the temperature of the source, T2 is the temperature of the sink and Tr is the temperature or inside temperature of the refractory surface. Second assumption is, now since you already know that in radiation heat transfer, the fraction of the surface which is seen by the sink is important because that will be only heated up. So, our assumption number 2, A1 can see no part of itself, no part of itself, and so we will also assume A2 also does not see any part of himself, any part of itself. That is the assumption number 2. The assumption number 3, that refractory surface AR, refractory surface whose area we have represented by AR, it does not allow heat loss. That means, that is, all the heat is re-radiated or reflected. That is, essentially we are considering a refractory surface is an adiabatic wall which does not allow any heat to be transferred from inside of the furnace to the outside. So, that means whatever amount of heat which falls on the area AR, it will be either re-radiated or reflected. Fourth assumption at the moment is A1 and A2 are black surfaces, or black surfaces. So, now what this figure represent is, this is a combined, direct and indirect, heat exchange between the surfaces, How it is direct? Say a source, it will radiate its energy Q12, that is the direct heat exchange between the source and the sink, and part of the heat will be reflected by refractory surface which is emitted from source 1. So, this is Q1 and R, and similarly when A2 gets heated up, it will also radiate its energy, and on account of which we will say this one is QR2. That I will be explaining this thing further. So, now let us see now, say of the total energy leaving from A1 to A2, A2, because A1 is at higher temperature, it is the source, and A2 is the sink. So, the amount of energy will leave from A1 and will strike at A2. So, what will happen? Out of this total energy, say some fraction of energy is absorbed by A2, and will be controlled by which factor? By the view factor, by let us say FB, where FB is the fraction of energy which is absorbed by the surface A2. So, FB in fact is a geometrical view factor considering the black surface. So, FB in fact will control the amount of energy that is absorbed by A2 as a result of radiation from the source A1. So, that is the FB is a very important factor, as I said. This is the view factor between the surface A1 and A2, or in physical sense it is the fraction of the surface which is seen by A2 by the radiation which is coming from A1. So, when FB energy is absorbed, that means 1 minus FB is intercepted by AR, Now, as the energy will be emitted by A1 to A2, A2 will absorb the energy and it will also be heated up. So, after a while A2 will also begin to radiate the energy, and again in the same way we can write, say, of the total energy leaving from A2, again fraction will be absorbed by A1 and rest will be intercepted or intercepted by refractory surface AR. Now, as FB is the view factor from A1 to A2, similarly we say that let F dash B is a view factor as seen by A1 with reference to A2. So, that way the fraction F dash B is absorbed by A1, and 1 minus F dash B, that will be intercepted by AR. Now, there is a relation between FB and F dash B. So, the relation between FB and F dash B, FB and F dash B is FB into A1, that is equal to F dash B into A2. Therefore, F dash B can be expressed in terms of FB, that is into A1 upon A2. So, with this it means, say now, of the total energy leaving from A2, say FB into A1 upon A2 will be absorbed by A1, and 1 minus FB into A1 upon A2 will be intercepted by refractory surface AR. Now, you are seeing that the role of refractory surface. So, accordingly, the direct heat exchange heat exchange between A1 and AR and between A2 and AR are given by the following expression, are given by the following expressions. So, we can write down now, say Q1 to R, that will be equal to 5.67 1 minus FB into A1 T1 upon 100 to the power 4 minus, remember here it is TR because we are considering an exchange between A1 and AR, 100 raised to the power 4, and let us call this expression to be number 1. Similarly, Q2 to R, that will be equal to 5.67 1 minus FB into A1 upon A2 into A2, this will be A1 T2 upon 100 raised to the power 4 minus TR to the power 4 raised TR upon 100 raised to the power 4. Let us call this expression is number 2. Now, we have assumed that there is no heat flow to the refractory. That means there is no heat loss from the inside of the refractory to the environment. That means we have considered adiabatic wall, and the result of this assumption we can write down Q1 to R plus Q2 to R, that is equal to 0. This is our expression number 3. So, we can solve now, solving equation 1, 2 and 3, solving 1, 2 and 3 simultaneously for TR. This exercise I leave it to you, please do it. So, we can get the value of TR, that is equal to 4th root of A1 minus FB into A1 T1 to the power 4 plus A2 minus FB A1 T2 to the power 4 divide by A2 plus A1 minus 2FB into A1. This is expression number 4. So, this particular expression gives you the temperature of the refractory surface, which is due to net exchange of heat from A1 to A2 and A2 to A1. So, now then we can, now further we can write down say Q1 to R, that is equal to minus Q2 to R, and that is equal to say 5.67 into A1 minus FB into A1, A2 minus FB into A1 upon A1 plus A2 minus 2FB into A1 T1 upon 100 to the power 4 minus T2 upon 100 to the power 4. Let us call this expression number 5. Now, this particular equation 5 says that this is the additional indirect heat exchange between A1 and AR. That means this particular expression suggests you that there is an additional heat exchange will occur from the surfaces A1 and A2, which is obtained by reflection and re-radiation by AR. So, the role of refractory surface now becomes very clear. It gives you the additional amount of energy by reflection from surfaces A1 and A2. So, now the total heat flow that will be equal to heat from direct exchange that is equal to Q1 to 2 plus heat from indirect exchange. Heat from indirect exchange. So, that will be, let us say, equal to Q1 to R. So, therefore, total amount of Q that will be equal to Q1 to 2 plus Q1 to R. Q1 to 2 that is equal to 5.67 FB A1 T1 upon 100 to the power 4 minus T2 upon 100 raised to the power 4. So, let me call this is expression number 6, this is expression number 7. Now, if I add 5, 6 and 7, now I have to add it, then I will be getting the heat, total amount of heat that will be equal to, that is by adding 5, 6 and 7 and rearranging, we get Q 5.67 into F BR into A1 T1 upon 100 to the power 4 minus T2 upon 100 raised to the power 4, and let this equation be number 8. So, here in equation 8, say in equation 8, FBR that is equal to A2 upon A1 minus FB square upon 1 plus A2 upon A1 minus 2FB, and this is called, so FBR is a composite geometrical factor, for the closed system, of two heat exchanging surfaces, formed by A1 and A2. So, in short, what this FBR has a physical meaning is that it rather modifies the view factor as formed by surfaces A1 and A2. So, now the role of refractory surface is very clear. That means, the refractory surface, it provides an additional amount of heat exchange, or which is coming through re-radiation or by the reflection from the refractory surfaces. Therefore, the refractory surfaces are very important. So, from here we can derive some of the say important limiting cases. So, we can derive now say some of the important limiting phases, some of the important limiting cases. Now, what we can from here we can see what is the role of refractory surfaces. Now, let us take an example. Now, before this, the assumptions of deriving this information for some of the important limiting cases, there are certain assumptions. Assumption number 1, refractory, say assumption number 1, heat flow through the refractory is negligible. Flow through the refractory is negligible. That is the assumption number 1. And second, refractory and exchanging surfaces, refractory and exchanging surfaces must form a complete heat exchanger, a complete heat exchanger. So, under these two assumptions, if we consider some of the limiting cases, let us see what these limiting cases could be. Now, for example, let us consider this is say one surface A1 and this is the another surface A2. Now, this is say enclosed by a refractory wall or a refractory surface. So, this is a refractory surface So, this is the refractory surface and which encloses say surface A1 and another surface is A2. Now, let us take say in this case let us take it for example A2 upon A1 if that is equal to 1, right. Say both area is the same. So, in that case FB that is equal to 0 because both cannot see each other. So, in that case we can derive the value of FBR, that is FBR that is equal to, we have just now derived the formula A2 upon A1 minus FB square upon 1 plus A2 upon A1 minus 2 FB. So, we substitute A2 upon A1 is equal to 1 and FB is equal to 0, then we get the value of FBR that is equal to 0.5. So, you see the value of FBR, it also depends upon the area ratio of A2 and A1 and also it depends upon what is the value of FB, that is what fraction of the surfaces can be seen by A2 with reference to A1 or A1 with reference to A2. This is one particular example. Let us take another example. Say in this case, let us take this one is the area A1. This is area A1. Take this is area A2, this is area A2, and they are enclosed by a refractory wall. This is the refractory wall. This is the refractory wall, and the area, they are the A1 and 2 enclosed by the refractory wall. Now, here we have say A2 upon A1 is still equal to 1. Now, here FB is not equal to 0 because of the arrangement of the two surfaces. So, therefore, it is equally important how the two surfaces are arranged in order to get the beneficial effect of refractory surface. So, here if FB is not equal to 0, then we can calculate again say FBR, that will be equal to say 1 minus FB square upon 2 minus 2 FB. All that I have to substitute the value of A2 by A1. So, if I solve this thing, that will become 1 minus FB into 1 plus FB upon 2 into 1 minus FB. So, 1 minus FB cancels out. So, here FBR, that is equal to 0.5 plus FB upon 2. So, you see the value of FBR now here, it further depends upon FB, that is how the two plate surfaces or how the two source and sink they are arranged with reference to each other. Now, this situation can also be perceived to be say if this is the say area A1, this is say area A2, and enclosed by a enclosure, the refractory enclosure, say here also A2 upon A1 is equal to 1. So, here also the same relationship between FBR and FB holds good. Now, remember this FB, it concerns to the black surfaces. That means the emissivity of a black surface is equal to 1. We have not yet considered the influence of emissivity of the real surfaces. Now, let us take another example. Say for example, I take now say this is the A2 and somewhere here I have A1 and it is enclosed by a refractory like this. This again a refractory enclosure. So, here let me consider now a case where A2 upon A1 that is equal to infinity. That means either A2 is very large, so I mean this is A2. So, A2 by A1 infinity means either A2 is very large or A1 is very small. In both cases A2 by A1 it tends to infinity. Now, if we substitute these values into our expression FBR is equal to so and so. So, we will be getting FBR that tends to equal to 1. So, these are the say some of the limiting cases of the arrangement of source and sink within the refractory enclosure. Now, so far we have considered the Blake surfaces only. Now, if we want to consider the real surfaces, then we have to define a term which is called emissivity. Now, as I have said, so far we have considered black surfaces, that surface A1 was black, A2 was black. Now, let us consider the heat transfer between gray surfaces. Heat transfer between gray surfaces, and it is defined by, the surface is defined by, say, a term emissivity. This emissivity, that is equal to, say, radiation of heat from a gray body, radiation of heat from a gray body divided by radiation of heat, radiation of heat from a black body. So, by introducing the term emissivity, we can determine an expression for heat transfer between two gray surfaces, and that we will write, say, Q, that is equal to 5.67 into F into A1 upon T1 upon 100 to the power 4 minus T2 upon 100 to the power 4. Now, remember, here the effect of emissivity of surfaces we have embedded in a parameter f, which is the view factor, and we are now considering that view factor will also be influenced by the presence of emissivity in such a way, so that the value of f, that is equal to 1 upon FBr plus 1 upon epsilon 1 minus 1 plus A1 upon A2 1 upon epsilon 2 minus 1, where epsilon 1 and epsilon 2 are the emissivity of the surface 1 and surface 2. Now, whether this expression is correct or not, if we put, say, epsilon 1 equal to epsilon 2 equal to 1, that is that of the black body, then our expression f, that is equal to FBr, and hence we can say that what formulation we have made for the calculation of f is correct, because it is giving us the value of f, that is equal to FBr, when the A1 and A2 are enclosed by black surfaces. So, what is involved in calculation of heat transfer by radiation? So, what we can do now, say, general procedure to calculate the rate of heat transfer between the two surfaces within a furnace. We can do this way, that is, number 1, first of all we represent furnace conditions and geometry. We represent furnace conditions and geometry by a two-zone system, which incorporates A1 and A2, or three-zone which incorporate A1, A2 and AR. Two-zone or three-zone model, and we estimate T1, T2, A1, A2, epsilon 1 and epsilon 2. Then second, we estimate or find the value of FB. Once you know the value of FB and A2 by A1, then calculate FBR. Then calculate FBR. Once you calculate FBR, now you can calculate F. Now you can calculate F, and once you know the value of F, then you can calculate Q. However, this is the way in which you can calculate the heat transfer between the two real surfaces enclosed by the refractory surface. However, I will try to illustrate with a problem to calculate the heat transfer. Now, so far we have considered the heat transfer by radiation. Now, in this is also important about the gas radiation. Gas radiation, because flame is a product of combustion, and it is well known that all diatomic gases like nitrogen, oxygen, they neither radiate nor transmit any amount of energy. So, heat transfer by all diatomic gases, it occurs by the mechanism like convection, whereas all triatomic gases, they emit or radiate heat within certain wavelength. So, in considering the heat transfer by radiation from products of combustion, it is important to consider the radiative heat exchange between a body of gas and a black enclosing surface, for example. So, what we will be considering, so let us consider a body of the gas. Let us consider the body of the gas at temperature Tg, which is enclosed this is the refractory. This one is the body of gas which is at temperature Tg, and the refractory surface enclosure has a temperature Ts. Area of the body of the gas, let us say Ag, and this L, so what we say L, that is the characteristic linear dimension of the body of the gas. Ag is the area of enclosing surface. Enclosing surface. Tg is the temperature of body of gas, whereas Tr at Ts, that is equal to the temperature of enclosing surface. Enclosing surface. So, in fact, this diagram is the gas body and enclosing surface, and enclosing surface, the heat transfer or the heat radiation will occur from the gas which is at temperature Tg, and it will heat up the enclosure. Now, remember, this heat transfer by radiation is important only when the products of combustion contains triatomic gases, because the triatomic gases like CO2, H2O, they emit or radiates heat within the particular wavelength. Nitrogen and oxygen, they are transparent, they neither emit nor radiate. So, in a flame which consists of the nitrogen, oxygen, H2O and CO2, H2O and CO2, they emit or radiate the amount of energy. That point is to be important. Only triatomic gases, they emit or radiate the energy within particular wavelength. That is, the temperature is also an important issue. So, in order to define in order to calculate this, what we do is that we calculate size L, of the gas body, and this size L is given by 3.6 upon volume of gas divided by surface area. Now, once we have found out from the volume of gas and surface area the value of L, then let us consider P, that is the partial pressure in atmosphere of the absorbing gas. Now, the proportion of radiant energy absorbed will depend upon the number of molecules in the path of the beam. That means, depending on the number of molecules of the gas, naturally the amount of radiation will depend upon how many numbers of molecules of that particular gas is present. For example, if we have a mixture of CO2, H2O, N2 and O2, so we have to find out how many number of molecules of CO2 is present, because only those numbers will decide what is the amount of heat is being transferred. Now, at a given temperature, this number of molecule that determines the heat transfer by radiation is proportional to P into L, where P is the partial pressure of that particular gas. That means, from the composition of the products of combustion, you will determine what is the value of partial pressure of that particular gas. That is, if the total pressure is equal to 1, you will find out the concentration of CO2 or H2O and then find out the partial pressure of CO2 if CO2 is under consideration, H2O if H2O is under consideration. Then, now from here on, one has to use the plots. That means, now once you find out the value of P and L, that is for water or for H2O, then from here the emissivity of these gases, are given as a function of temperature, for different values of P into L. That means, and the plots, they are something like this. That is, the plots are there where say gas emissivity, for example, for CO2, that is as a function of temperature, and I am just showing the schematic. So, these plots are like this and they are shown as a function of P into L. Now, for the exact nature of the plot, I will request you to consult a book by J.P. Holman, Heat Transfer, 8th edition, page 438. These diagrams are given, and from these diagrams the value of emissivity can be determined. How will you determine? That is, from a composition of products of combustion, you will be determining first of all PCO2 and PH2O. From POC, this can be easily determined. Now, once you determine this, then find out the value of L from the relation which I given you earlier. Make product P into L. Then consult the plots for gas emissivity for CO2 as well as H2O, and as a function of temperature, you will, as a function of temperature, and for a given value of P into CO2, P into L, that is PCO2 into L, you will read the value of emissivity of CO2. Similarly, same way you can do emissivity of H2O. However, you have to consult the CO2 and H2O independent diagram. So, therefore, then epsilon dash G, that will be equal to epsilon CO2 plus epsilon H2O in case of when products of combustion consist of CO2 and H2O. Then the heat transfer Q, that is equal to 5.67 1 upon epsilon dash G plus 1 upon epsilon S minus 1 into AG TG upon 100 to the power 4 minus TS upon 100 to the power 4, where epsilon S is the emissivity of surface. Emissivity of surface, and epsilon dash G is the emissivity of the gas body. Emissivity of gas body. Tg is the temperature of the gas and Ts is the temperature of the sink. Ag is the area of the gas body. So, utilizing this expression, one can find out how much amount of heat will be transferred from the products of combustion when it consists of CO2 and H2O. That is, you can find out the rate of heat transfer or rate of heat radiation or radiative heat transfer from gas to the body. In the next lecture, I will be considering the problems and their solution depending on the use of these expressions.